All right, looks like we're live. Well, thanks everybody for joining us today. I asked everybody on YouTube to tell us where you're joining us from. I'm looking forward to this event. This is going to be a very exciting event. We have a very, very exciting talk planned, but also on top of that, we have some really fun trivia that we're going to go together. And then finally, we're going to also try to take a virtual tour of the sky. And that allows us to ignore the clouds, which is a lot more fun because then you get to see things in space and not just the Earth's atmosphere. So let me just introduce myself. I am Nick Aurora. I am one of the Queen's Observatory coordinator. The other observatory coordinator is also present, Connor Stone. He's going to be running the virtual observatory session later on. But yeah, before I get started, I would just like to acknowledge that both Queen's University, Queen's Observatory, and actually my own house are situated on traditional Anishinaabe and Haudenosaunee territories. In times like these, I'm actually very honored to be able to play, learn, grow as a human being, but not only that, remain safe and healthy. I acknowledge and greatly respect the territory's significance for the people who live here and continue to live upon it, and whose practices and spiritualities are tied to these lands, and they continue to develop in this relationship to the territory and its other inhabitants. Yeah. Okay, so let's get the show started. Before I introduce our speaker today, I would like to acknowledge sort of the institutes that are a part of this open house or this space trivia event. So we have the Arthur B. McDonald Canadian Astroparticle Research Institute, if I am getting the whole thing right. But in short, it's called the McDonald Institute, who's been a terrific part of not only organizing the open houses when we were able to meet together, but they continue to be involved in the space trivia as well. Then of course, there's Queen's Observatory, which Connor and I are a part of. There's Astronomy on Tap Kingston, which is also something we run as a public outreach event in bars, or now at your own house, where you have to bring your own beer. We're planning the next event to be on August 14th, so be sure you have your beers ready and join us in time. Then there's Queen's Observatory, where all of these, Queen's University rather, where all of these institutes are associated with. And finally, without the help and contribution from the Royal Astronomical Society of Canada, Kingston Center, none of this would be possible. So I would like to acknowledge their great contribution. Yeah, okay. So we're gonna start our night today with a talk from a graduate student here at Queen's, if I can get the technology going. Yeah. He is Dilraj Ghuman. He's a graduate student in the Astroparticle Research Group. He graduated with an honors Bachelor's of Science in Physics from University of Waterloo. After that, he actually went around to work at multiple different places, such as Snow Lab, which is up in Sudbury, which most people hear about if you've ever been to any of our open houses, and also Triumph, which is out west, Vancouver, if I'm not wrong. He worked on various experiments such as Deep 3600 and T2K, all of which are currently looking for dark matter. But right now he's involved in the upcoming P1 experiment, and that's what he's going to tell us about. So Dilraj, if you mind turning on your video and audio, I'm gonna stop my share. And yeah, take it away.
Okay, I'm gonna start sharing my screen. Okay, so let's get right into it. So first, we're going to start by breaking down the title. So what exactly are neutrinos? Now, this is a difficult question to answer, and scientists have earned Nobel Prizes in the pursuit of this. So, I mean, let's try taking a stab at it, though. So in particular, we know that neutrinos are actually fundamental particles. So these things, they can't be broken down any further. And we also know that they're weakly interacting. And that's just to say that they interact via the weak force, and they don't interact very often. And the third thing we need to know is that they oscillate. Now, this third component is probably the most complicated part. And the reason it's complicated is to think of it analogously. Say you and your friend were playing, I don't know, catch, and they were throwing a tennis ball or a baseball. Then as the baseball is traveling, at some point, it could transform into a tennis ball. And that'd be the equivalent of what's happening with these neutrinos. They oscillate between these three flavors of electron, muon, and tau, and the actual oscillation is quite complicated. But it'd be as if this baseball is transforming into a tennis ball. But for now, let's ignore that third component because it's not necessarily important to us when we're talking about astronomy. In particular for us, the most important part is actually the weak interaction, or the weakly interacting component. So what do I mean when I say weakly interacting? Well, we know what interacting means, mostly, but what does it mean by weakly? Well, there are two parts to this. We have the weak force, one of the fundamental forces. That's the force through which we have our neutrinos interacting in the first place. And we have the fact that it's also a rare interaction. So this interaction doesn't occur very often. In particular, for us in astronomy, we want to focus on this rare interaction. The weak force, of course, is important. That's quite complicated, so we'll ignore it for now. So I've started to talk about neutrinos, but everyone here probably wants to hear about astronomy. So let's take a bit of a detour before I continue and to explain and motivate why I'm talking about neutrinos. Okay, so I'm going to open up a link here. Move that, okay? And so this is a picture of or an image of the Milky Way. Now this is the image of the Milky Way just with our visible light. Now if we were to change this, say to X-ray, we'll notice that the image has changed a lot. And the structures that we see that are emerging are different than what we saw when we were looking at it via visible spectra. And again, we can change that to the gamma rays. And as we see that as we flip between these different wavelengths of light, we get different structures emerging. Now, the reason this is key is that you can actually think of our neutrinos as another way of observing the universe. And so you can see in this plot, or in this picture, that gamma rays can easily be obstructed as they travel, gamma rays being our light. But neutrinos, because we know they're weakly interacting and they're rare, they won't interact at all until we know that if we've observed them, they haven't interacted till that point. And so these provide a unique way of probing the universe that light may not be able to. But let's go one step further and let's look at another example. Suppose we're looking at our solar system just with the sun. Now, of course, this isn't to scale, but some common thing that a lot of people know is that the light from the surface of the sun takes about 8 minutes to travel to us. But what if I wanted to look at the center of the sun? So it's easy enough to produce images of the surface, but what does the center of the sun look like? Well, suppose you wanted to use light. Okay, so our journey begins at the center. And we're going to say, all right, there's some light or photon being produced somewhere at the center here. That photon's going to travel for a bit, but then it's going to collide with something because the sun is quite dense. There's a lot of going on in there. So it's going to hit something. It'll be absorbed and then re-emitted again in a different direction. But it happens again because of how dense the sun is. And so this path it's taking, sometimes referred to as a random walk, occurs many, many times in the sun before eventually it reaches the surface and then takes the 8 minutes we expect it to take. However, this random walk process can take anywhere from 10,000 to 170,000 years. It's a long time to wait for the light to get to us. And it's not a particularly useful way of probing the center of the sun. Now, instead, if we talk about neutrinos, well, those guys will travel directly through the sun because it doesn't see anything else. And so if we picked up a neutrino from the sun, we know it must have traveled directly through everything. And so it's a useful way to probe the center of the sun. Okay, now, in order to actually use neutrinos as things we can detect, we have to be able to detect them. So we're going to talk about the interaction here. So here I've denoted my neutrino as using this Greek character nu, with its flavor as just an L. So this neutrino is going to come in, it's going to interact with something in some interaction we don't know that happens, and it'll spit two things out. Now, one of those things will be a corresponding lepton. So what we can do is we can detect this lepton and know that it was produced from this corresponding neutrino. And this occurs with every flavor of the neutrinos. When a neutrino interacts, it'll produce the corresponding lepton. Now, unless you've done particle physics or have any background in that, these characters don't really mean much to you, especially muon and tau, because electron, most everyone knows about that. So we're going to look at a bit of an analogy in this case. Suppose instead of neutrinos, we're going to replace these guys with timbits. And the leptons we replace with donuts. So what we're saying is that our timbits that we want to detect will produce the same flavored donut that we can't detect. So then look at our interaction like this then. Well, we can replace all the neutrinos with that. So looking at this interaction, we see suddenly if we want to detect a certain flavored timbit, we'd have to look for the corresponding flavored donut. Okay, cool. But how do we detect these donuts? Well, this is where we talk about the high energy part of the title. These donuts are traveling really fast, right? Because they're produced by high energy timbits. And so when we talk about things traveling fast, one of the things that comes to mind are things like the sonic boom, right? So a sonic boom is when an aircraft or anything travels very quickly in air and produces a loud bang. And you can see a jet here producing that sonic boom. The same thing can happen with our donuts. When these travel in a medium, such as water, very quickly, they produce what's called Cherenkov radiation, or light. And you can see an image of that to the right, where we have Cherenkov radiation being produced. And so this light we can pick up. Okay, so we have a way of detecting our donuts, and we have a way of understanding which donuts correspond with which timbits. So how do we actually, what would we need in a detector? Well, we need a large volume or target mass because we know that these timbits rarely interact. So the larger the volume, the more likely we are to catch this timbit. Now we need the medium to be clear enough for light to travel, because light is what we're using to see what kind of donut we have. But we also want shielding from external events. Now this shielding is to block out any donuts that don't correspond to the timbit. Because cosmic rays, we have a bunch of quote unquote donuts floating around in space. We don't want to pick those up instead. So let's take a look at a couple of experiments that do already do this. So we have IceCube, which is relatively well known. This is an experiment at the South Pole that uses ice as its medium. And so you can see for scale here, we have the Eiffel Tower. So it's quite the massive experiment, as we would need it to be. And they're using little cameras to pick up on this Cherenkov radiation that's happening in the ice. Now, ice isn't the only thing we can use. We can use water as well. And so here you see KM3net, and we have Antares. And so these are both experiments near the Mediterranean that are using water as a Cherenkov source. Now, you may be wondering, well, why would we want to do the same thing in Canada? Or how would we even do it? Well, I'll answer the how first and answer the why later. As for how, well, we already have all the infrastructure set up. We have ONC for us. So ONC is Ocean Networks Canada. It's an endeavor that looks into exploring the ocean and what's happening with the ocean. Now, they've already set up all the infrastructure. So all this cabling is already done for us. So if we look at the previous water experiments, like these guys, like Antares and KM3net, we see that all the wiring here must have taken time and must have been done manually explicitly for this experiment. Whereas for us, if we were to build a detector in one of these areas here, we see that all the wiring and everything, all the infrastructure is built for us. So it's a huge benefit for us. We have all the infrastructure ready, and ONC happens to be one of the world's largest and most advanced cable ocean observatories anyways. And it's a great location. Now, this last point I'll get to later on, but for now we have the infrastructure ready. So we're ready to experiment. And that's what we're doing. We've already started testing. So current progress we've had with STRAW, which is strings for absorption length in water. These are two testing strings that we're using to figure out how light is behaving in the water. Because if you remember, in order to detect our donuts, we need to know what kind of light in Cherenkov is being produced. So we have 5 SDOMs on these strings and 3 POCAMs. So an SDOM is just a fancy camera. It's a camera that's hypersensitive to light, and we have cameras facing both directions, and we have 5 of those guys. POCAMs are just fancy LEDs. These guys are used to calibrate each of these cameras. So what happens is we have 3 POCAMs, one here, and one here, and the remaining are SDOMs. Now these POCAMs can emit light And we know, because we know the location and we can decide what color and power of light to emit, we can see how each of these cameras reacts. And if one of them reacts poorly, we know that it's giving us false information. So cool. What kind of results have we gotten so far? Well, as we can see, in this first plot here, at the top we have data from straw. So these are the hybrid cameras, that the light they're picking up. At the bottom, here we have data from ONC. Now what this is saying is that ONC is seeing current increase, and current increase just means that the water is moving quickly, and that's correlated with an abundance of light we see in our cameras. Now, that means that our bioluminescence is correlated with the current. So there are fish or some kind of biotic life that emits light when it moves quickly. Now this is a good and bad thing. Bad because of course you don't want any kind of background messing with our data. But this is good because we can correlate it with the speed. And so if we see something in our detector, we first have to ask ourselves, is it emitted by a fish or by some biotic life? And in that case, we can go to ONC and say, okay, what kind of speed or what kind of current were they experiencing? And then the plot on the right is something done to look at the clarity of water. And we get an idea that the water is relatively clear, mostly because we wouldn't want any obstructions in our light. Okay, now for the future. Well, the goal is to be able to further deploy a second test called Straw B. Now this has been delayed, unfortunately, because the goal was to deploy this summer, but because of recent events, it's been pushed back. But the goal of this was to learn more about the backgrounds and the water properties. Because we can add more detectors to these strings, we can get a better idea of what's happening in the water and how light behaves. So as of now, the timeline, the construction is complete, and we plan on deploying in the fall, and the equipment's been on its way, it's been shipped. Okay, so once all the testing is done, the final goal is to be able to build a full-blown detector. Now, this left image here shows what a preliminary form of the detector would look like. So we'd have these same lines that we've been looking at before, going into the ocean, except now we have detectors along the line and some POCAMs, which are the LEDs, to help to calibrate each of them. So you have around 10 detectors on each line. And then each line will have 10 of those to form an array. And so this array will be a part of our detector. Now, for a longer term goal, we would like to have multiple versions of these guys. And so if you have 3, 4, or 5 or 6 of them, we can get a much larger detector for free. If you remember, the larger our volume, the better we are at picking up these timbits or donuts. Okay, so now, why is the location good? So I've explained to you why we have all the infrastructure, but why would we want to build it in the first place? Well, suppose you have a telescope here, a neutrino telescope in the north. Okay, well, you'd expect, like any astronomer, you'd expect to look into the sky to look for these timbits. The issue, however, is that if you look into the sky for timbits, you're also going to find a bunch of donuts that weren't produced from those timbits, the cosmic rays. And how exactly do we deal with that? Well, it's not easy to distinguish between those. So we have to think with the neutrinos. You have to remember that these timbits, or neutrinos, can also travel through the Earth for free. So we can actually look down, and we look through the Earth. And so while those timbits are traveling for free through the Earth, our cosmic rays aren't. And so if we do this for a bunch of our detectors, we get this global pattern. And so you see that there's a couple of detectors already that I mentioned that are here, and we have Ice Cube in the south. We have nothing in the west here. And so if we were to build P1, or the experiment that I've been talking about, we'd be able to add coverage to our neutrino detectors around the world. And so where the detectors in the east are detecting particular portions of the sky, as denoted by these arcing fashions across the galactic plane, P1 would provide areas that aren't covered by these detectors. And so that could, so together with all of these detectors, we can get a global coverage of the sky with neutrino detectors. Okay, so let's look forward to the future. Construction is near, and once we've done testing, we can hopefully start building stuff. And hopefully we'll get some results following that, and maybe we'll have some donuts to celebrate. So I'll be taking any questions now, and thank you for listening.
Wow, Dilraj, thank you so much for actually doing this presentation. Yeah, we do have a few questions coming in from the audience. I would like to remind the audience already that if you have questions, type them in the YouTube chat while we're going through this discussion, and Dilraj will answer them for sure. If I say them out loud, that is. Okay, so let's get straight to the question. So Connor asks, on slide 19, if you go to your talk, can you get interference with your experiment by being so close to the already built infrastructure?
So like these guys here?
Yeah, essentially.
Okay.
Or if you go back to Antares or KM3net, there you say the advantage of having ONC is that there's already infrastructure there. But are there some disadvantages from that?
So I mean, for example, with KM3net and with Antares, their disadvantages were that they had to actually build all of this infrastructure. And with ONC, we have that. As for these other like experiments going on here, there shouldn't be any interference just because of the distance. Any of the light produced from these guys won't be able to make it to Cascadia Basin, which is where we're looking to build a detector anyway.
Okay, great. Awesome. Then apparently this guy, Mark Richardson, he seems to have quite a few questions for you. Right, okay, so here we go on almost a trail of what Mark Richardson has to say. First question from Mark Richardson is, do we see light related to currents in other parts of the world?
In other parts of
the world. So you showed a plot of bioluminescence and how that corresponds to currents. Mark's question is, well, that is for the Pacific Ocean. Have the people in Mediterranean noticed the same thing as well?
I see. Yeah. So the experiments like in Antares and KM3net, they have noticed bioluminescence like that as well. But also because they're in the Mediterranean, they do have light that's not necessarily correlated with the current. So they do have more difficulty in discerning the background because of in that way. And that is also a benefit of being in the Pacific, is that our light isn't the background isn't as obstructive as it is for experiments in the Mediterranean.
Awesome. Yeah, I think this next question is pretty interesting. From Mark again. If you already have ice cube detector, what's the benefit of making P1?
Okay, so that's a good question, actually. So that leads us to this last slide I had. Oh, we'll do that. Okay. So ice cube in particular can only scan so much of the sky for neutrinos, right? And so because ice cube is down here, this brown strip here is what it would cover in terms of the neutrinos traveling through the Earth. Now the experiments in the east also do have similar kind of coverages in terms of these colors. These are the colors that are non-blue. Now, if you wanted a full coverage of the sky for neutrinos, because you want to be able to track neutrinos coming from any direction, building an experiment like P1 would provide coverage that doesn't exist from the other detectors. So the main reason behind this detector is because it would provide more coverage.
I see. Also, like maybe I should add a question to Mark's question over here as well. I'm wondering, ice cube works with ice, and you have P1 in water. And is there a difference in sensitivity, or are the sensitivities exactly the same?
So it's a good question. Light travels differently when you're talking about in ice or water. So the sensitivities definitely change. And also the way that the light behaves is going to be different as well. So the detectors, like for example, with ice cube, the benefit was that the ice here is ultra pure. So because it hasn't been touched in so long, light won't get obstructed as often. But the issue with having ice is that ice is also layered. And so because ice is layered, you'll have little cracks in the ice as well. And so you have to account for those, for the light changing as it goes through the ice. With water, the benefit is that you won't expect those layers to occur.
Yeah.
But again, you also have other issues that arise when you're using water. So there are benefits to having both.
I see. Yeah, I guess the calculations to account for those cracks are not easy, I'm guessing. Right. So we're still on the Mark trail, but I promise this is the last question, I think, from Mark. He asked, if neutrinos go through the Earth, how do they interact with the detector?
Okay. So let's see. It's a good question. So neutrinos, well, we don't decide when they interact, of course, right? Neutrinos will interact when just almost randomly. But the hope is that if we have trillions of neutrinos flying through us every second, if one of them does interact, we hope that it happens to interact in the detector. And so it's like having a river and trying to make as big of a net as possible. The bigger your net, the more likely you are to catch those fish. But where those fish get caught aren't exactly, dependent on you. There could be a fisher up ahead that catches it. Those neutrinos could interact in the Earth. But if they interact where we are detecting them, then we know they've traveled through the Earth without interacting.
Okay. Once again, I'll add another question to Mark's question again. Could you give us an estimate of how many neutrinos you expect to see per hour, per year? With P1 at least?
I can't remember the number off the top of my head. But annually, I think Ice Cube, for example, sees maybe 30-ish neutrinos a year.
Oh, wow. Okay, so very rare.
Yeah, I wouldn't quote that. But yeah, you don't expect to see very many.
Right. Oh, okay. All right, so a final few questions. This one's from Adam. He asks, is there a plan to combine P1 data with other neutrino observatories to create better bounds on the neutrino signature?
Yeah, I mean, that's kind of the hope with this global coverage idea, is that if you can combine all the data, so like for these, where these, for example, where these detectors overlap, like these areas here, you can combine their data and compare them to get more restrictions on the properties of these neutrinos. So yeah, absolutely, yes.
Okay, and I think this is the last question because we're slightly running out of time. This is from Simran. Her question is, why can Ice Cube only see neutrinos from the small dark burgundy line? So on this plot, why is Ice Cube only the small dark burgundy line?
Right, so when you're looking at the geometry of these detectors, you don't want your neutrinos to be, well, at least for high energy neutrinos, you don't want them to be traveling directly along the lines because they wouldn't be as discernible. And so what's easier is to look at, so if I went to this plot here, so this is a bit misleading because I made it look like it was going directly opposite or directly into the Earth. What we're more expecting from high energy neutrinos is for them to travel almost along the surface. And so it's still providing that kind of filter with the Earth, but it's not being sent directly through the Earth from the opposite direction. And so because of that, the actual coverage isn't going to be, so for example, with Ice Cube here, you wouldn't expect the coverage to actually be the North Pole. Instead, for high energy neutrinos, the coverage is along the equator. And that's true for every detector here. Right? You'll notice with P1, it isn't exactly the opposite side. You kind of have this strip that goes almost at an angle to it.
I see. Oh, awesome. Well, thanks, Dilraj, for this very, very interesting talk and this final discussion with P1. I think this is definitely an exciting experiment, and I can't wait to see what kind of results this brings up. So thank you for coming out and enlightening us with P1.
Yeah, thank you for having me. Yeah. Stop sharing now.
Yeah. All right. Okay, so we are gonna go on to the trivia now. So I'm gonna try share my screen. And hopefully you guys will not see the trivia questions. Okay, here we go. Let's first go through some of the trivia instructions. First of the instructions is, of course, listen to what I am saying for each section. It is important to Okay, so Mark apparently has a question. I will answer that question later on. Yeah, it is important to listen to all the instructions to gain as many points as possible. So the trivia sheet is present in the YouTube descriptions. So it's also present now in the chat. So where you have your YouTube video, just go down, scroll down into the description of the video, and you'll see a link to download the trivia answer sheet. Not with the answers, where you fill in your answers. Of course, this time we made the trivia sheet fillable by a PDF software, so you can just type into it. As with any trivia, please do not look up the answers on the internet. Yeah, if you want me to repeat any questions, use the chat function present in YouTube, and I will try to do that. As I said before, not before, but yeah, as we said the last time, spellings are not the thing you're being graded on over here. So passable spellings are needed. And finally, I think the most important thing is to have fun. One thing that people like to do with trivia, I think this is a tradition, is to have a drink with you. I myself have some gin and tonic with me, but yeah, feel free to have any cold drink with you because it's a hot day, if you'd like. Cheers. All right, let's get started. Okay, so the first round of the trivia is a multiple choice round. There are about 10 questions, each with approximately 4 to 5 options. Listen to all the options. I'll repeat each question maybe once or twice, and then if I go too fast, please put it once again in the chat, and I'll repeat the needed question. Also, by the way, there's also an intermission later on, which is where you get the chance to go through the picture round, the word search in the trivia sheet, and there are also maybe 5 quick questions that you can answer. But you can also feel free, if you finish multiple choice round too early, to go there as well. All right, let's get started. Question number 1. During what phase is the moon least visible from the Earth? Is it the new moon, the full moon, the gibbous moon, or the secret moon? The secret moon is also sometimes known as the smoon. Yeah, so let's repeat the question once again. During what phase is the moon least visible from the Earth? So you guys have to think about where essentially is the sun shining on the moon and whether we get to see it or not. Is it the new moon, the full moon, the gibbous moon, or the secret moon? Also, I think this is also when the werewolves come out, the answer to this question. So think about, if you watch Twilight, think about that. Question number 2. This is from Star Wars. What were Darth Vader's last words to Luke Skywalker? Is it, remember me? Is it, may the force be with you? Is it, I'm so proud of you? Or is it, you were right? So from the famous film series, Star Wars, what were Darth Vader's last words to Luke Skywalker? Were they, remember me? Were they, may the force be with you? Something very, very prominent or very well known around the world when it comes to Star Wars. If you haven't watched Star Wars, I think you still also know this. Was it, I'm so proud of you, or was it, you were right? Question 3. What is the name of the pattern found in the structure of an iron meteorite? So the picture is shown over here, and we're asking you, what are these patterns called? They're mostly found in iron meteorites. Is it Chalcedony? It is Widmanstatten. Is it orthorhombic? It is Thagomizer. I would say whoever made these multiple choices did go an extra mile to come up with these options. Once again, let me repeat the question. What is the name of the pattern found in the structure of iron meteorites? Is it Chalcedony, Widmanstatten, orthorhombic, or Thagomizer? So the answer to this question is also related to how, well, the name itself is also a crater on the moon as well. I think on the east side of the moon, there's a crater, which is what these pirates share their name with. Question number 4. How far does the average person walk in their lifetime? And you have to answer this not in kilometers, but in other units. So option 1, 5 times around the Earth. 5 times around the moon. Option 2 is 5 times around the Earth. Option 3, 5 times around Jupiter. Or option 4, 5 Earth orbits around the sun. So essentially the distance that the Earth travels in a year around the sun. How far does the average person walk in their lifetime? 5 times around the moon, 5 times around the Earth, 5 times around Jupiter, 5 Earth orbits of the sun. Question number 5. How long does it take light to travel from the surface of the sun to the Earth? So we just learned using in Dilraj's talk that it takes about 170,000 maximum, 170,000 years for light from the center of the sun to reach to the surface. Now the question over here is, how long does it take from the surface to come to the Earth? Is it 8 seconds, 80 seconds, 8 minutes, or 80 minutes? How long does it take for light to travel from the surface of the sun to the Earth? 8 seconds, 80 seconds, 8 minutes, or 80 minutes? Question number 6. What is the name of Ripley's cat in Alien? Is it Jonesy, Scratch, Beaver, or Lambert? I'll repeat the question again. What is the name of Ripley's cat in the movie in Aliens? Is it Jonesy, Scratch, Beaver, or Lambert? I'll remind you again, if you guys need any questions repeated, you can put them in the chat and I will repeat them again from one section. Moving on to question number 7. When a planet appears to travel in the wrong direction on the sky, what is the motion called? So a few planets in our solar system, when you look at them in the evening, they appear to go in the wrong direction. And we're asking you, what is that motion called? Is it renegade motion, retrograde motion, reverse motion, or reggae motion? So Kevin commented saying, this is an awesome question. And I hope, Kevin, that you find this question awesome because of the multiple choices that are given over here. Once again, props to Connor, who made this question and came up with some really interesting multiple choices. So when a planet appears to travel in the wrong direction on the sky, what is the motion called? Renegade motion, retrograde motion, reverse motion, or reggae motion? Question number 8. How far is the Earth from the center of the Milky Way? Is it 25 light years, 250 light years, 2,500 light years, or 25,000 light years? How far is the Earth from the center of the Milky Way, which is where the supermassive black hole of the Milky Way sits, one of my favorite objects in the sky, although we can't see it from our naked eye? Is it 25 light years, 250 light years, 2,500 light years, or 25,000 light years? Question 9. In the movie Independence Day, while dragging an alien across the salt flats, actor Will Smith notably complains about what aspect of the alien? Smell, hair, teeth, or eyes? In the movie Independence Day, while dragging an alien across the salt flats, actor Will Smith notably complains about what aspect of the alien? I watched this movie when I was a very young kid, and I don't think I watched this movie in English. I think growing up in India, I watched this movie in Hindi, which is very interesting because I think the dubbing was different. Okay, so the options are, is it smell, hair, teeth, or eyes? Once again, in the movie Independence Day, while dragging an alien across the salt flats, actor Will Smith notably complains about what aspect of the alien? Smell, hair, teeth, or eyes? And the final question in the multiple choice round, Alpha Alpha is a classic example of bad acronyms in astronomy. What does this acronym stand for? Is it Arecibo Legacy Fast Alpha Survey, Alpha Waves at Low Frequency Array, a low frequency array for the Lick Frontiers Association, Antarctic L-band Far Ultraviolet Fast Telescope? So if you've ever been to any one of the open houses when you were able to go up to the telescope, one thing you will know is astronomers are very bad at naming instruments or even naming things. And this question is associated to how bad we are when it comes to naming things. Alpha Alpha is a classic example of a bad acronym in astronomy. And what does it stand for? Arecibo Legacy Fast Alpha Survey, Alvin Waves at Low Frequency Array, a low frequency array for the Lick Frontiers Association, Antarctic L-band Far Ultraviolet Fast Telescope. So this brings us to the end of the multiple choice round. Once again, I'll take about 10 seconds, maybe 20 seconds for you guys to comment if you guys want any questions in this round repeated. This is a reminder that each question, I think, is about 1 point. So there are 10 points on grab over here. But yeah, comment in the chat if you want any questions repeated. And while that happens, maybe I'll answer Mark's question. Nick Aurora, did your name has anything to do with you becoming an astronomer? No, not necessarily. I think my last name, although it very closely resembles the Aurora Borealis or the Northern Lights, it has nothing to do with that, unfortunately. I think, if I'm right, the meaning of my last name essentially means the other tribe. So in India, I come from the business class, and there used to be two business classes, one called the business class and the other one called the other business class. And that's what my name draws from, Aurora. I would like to think that I became an astronomer because my last name is Aurora, or there's nothing else for me to do in this world. All right, I think there are no need to repeat any questions. It looks like. So we're going to move on to the sound round. Okay, so this particular section contains about particular question contains about. I'm trying to make sure that you guys hear the sounds. Sorry, having a little technical issue here. All right, so okay, so we're going to play about 5 small clips of sounds, and you guys have to answer the question related that I ask about that sound. I have these questions written down, of course, and so I will open those questions. All right, here we go. I will play the whole sound round twice. There are 5 segments with about 5-second break in between. All right, so the first question is, name the character.
At last, after 2,000 years of work, the Illudium Q-36 explosive space modulator. At long last, my dream come true.
All right, so who was the character speaking in this particular sound clip? I'm hoping that you guys can actually listen to the sound as well. All right. Sound number 2. Name the movie from this sound, which this sound clip belongs to.
100 feet, you know what you're doing, right?
Yeah, I'm tapping on brakes a little bit.
Drop the nose, you're gonna lose it.
Knock it off. Drop the nose off.
All right, what's the airspeed?
200 is right on it.
What do you say we just drop that nose there? Like that. Smooth as a baby there.
That's impossible.
Well, for a computer, it might be.
This keeps happening. Sorry, guys. Once again, so name the movie from which that sound clip was taken. The third sound clip is from an astrophysical phenomena, but it also represents a particular experiment or a particular thing that we heard. So the sound is going to play for you 4 times, and you can either name what is it that we are hearing, or what astrophysical phenomena does this sound refer to. Here we go.
Possible.
Well, for a computer, it might be.
All right, so I think this happened about 2 years ago, and you have to name the astrophysical phenomena that made that sound. It caught a lot of attention. All right, the 4th sound is once again from a movie, and the question is to name the movie.
Ruth, what's the status on that computer?
She's right behind you, Mr. Harrison.
Does she handle analytic geometry?
Absolutely. And she speaks.
Yes, sir, I do.
Which one?
Both. Geometry and speaking.
All right, so name the movie from which the sound clip was taken from. This is a very, very famous movie, and there will be another question that will come very close to this movie. So name the movie from which this clip was taken from. All right, finally, sound number 5, which is the last sound. This is a song, and so for half a point each, name the song and the artist that produced the song. Here we go. All right, so for the last sound, the question is to name the song and the artist. Okay, so we're gonna go through the sounds once again. This is the first sound clip, and the question is to name the character that you're hearing.
At last, after 2,000 years of work, the Illudium Q-36 explosive space modulator. At long last, my dream come true.
All right, so once again, the question is to name the character in that sound clip. Moving on to the second sound clip, where you have to name the movie from which the sound clip is taken from.
100 feet, you know what you're doing, right?
Yeah, I'm tapping on brakes a little bit.
Drop the nose, you're gonna lose it.
Knock it off. Drop the nose on.
All right, what's the airspeed?
200, right on.
What do you say we just drop that nose there? Like that. Smooth as a baby there.
That's impossible.
Well, for a computer, it might be.
So, what movie was this sound clip taken from? Moving on to the third sound clip, where you have to name the astrophysical phenomena that causes this sound. So, what astrophysical phenomena causes this sound? All right, question number 4. This sound clip is also taken from a movie. Name the movie.
Ruth, what's the status on that computer?
She's right behind you, Mr. Harrison.
Does she handle analytic geometry?
Absolutely. And she speaks.
Yes, sir, I do.
Which one?
Both. Geometry and speaking.
All right, so name the movie from which the sound clip was. And finally, the fifth sound clip, which is where you get half a point for a 2-part question, which is name the song that I'm going to play and the artist that created the song. All right, so this brings us to the conclusion of our sound round. Next, we're going to take a 5-minute intermission. In this 5-minute intermission, there are a few things you can do. There are quick questions, about 5 of them, which you can try to answer. I think these are very interesting questions where each of the title that you see is synonymous to a movie, a scientific fiction movie, of course. So yeah, see if you can try to name the movies that we're referring to from these titles. So for example, Ferris Fellow means Iron Man. So what do these particular titles mean? Finally, you can also choose an adventure. So these are 4 different tracks that you can go. One of them is a very, very hard track. The other one's fairly easy. And the other 2 are kind of medium. The questions to these are actually gonna come later after the end of the general trivia. If you can also do a word search. This time, the word search is on notable astronomers who did something big. So we have Jim Peebles, who just won the Nobel Prize in cosmology last year. We have the Faber-Jackson relation, which is where you get standard Faber. You have Edmund Hubble, who came up with Hubble's law, which is what you be used to get distances to various galaxies. So you have to find the names of these scientists in the word search. And the first name and the last name are not together. So they are separate. Finally, there's also a picture round, which is 4 pictures. You have to name what you're seeing in the picture, except the first picture where you have to name the telescope in the background and the movie from which this picture was taken from. It is a very famous movie. In the second picture, you have to name the probe. Finally, in the third picture, name what nebula we're looking at. And in the fourth picture, the constellation So yeah, this is a 5-minute intermission. If you missed a question, you can also ask us to repeat a question, and I'd be happy to do that as well, either from the sound round or from the multiple choice question. Coming up next is the general trivia, which is where the training wheels are off, which means there are no multiple choice questions. So we'll ask you a question and expect an answer. Also, during this trivia, do feel free to tell us which of these particular questions up until now have been your favorite. Or if you would like to see a theme come up in the trivia round, and we can try to do them in some future events. Now, I've not been keeping track of time, or I don't know how long I've been speaking for in this intermission. So I'm gonna say there are about 2 minutes left in this intermission. And I'm hoping Connor, who's in the background, might correct me about this. Thank you, Connor. He said he'll time me for 2 minutes. Yeah, I think this is something very exciting that we're gonna do towards the end of the trivia. You're not required to stay, so if you want to leave, you can leave, but we're gonna try to have a virtual observatory session where Connor is gonna lead us through the software, where he's gonna show us things in the sky. There are a few advantages to this. I think one of the advantages is that we don't have to worry about the clouds. You get to see what you want to see. We can also change the location, so we don't have to stay in Kingston. We can go down to the southernmost point of Argentina and try to see the Southern Cross, or the large and the small Macedonian cloud. But I think the most interesting thing, in my opinion, and this is something I would love to do with Connor as well, he can turn back time and actually show you what the sky looked like on the day you were born, or any significant day that you can think of. So yeah, these are some very interesting things awaiting for us at the end of this trivia round. Okay, I think we are good. There are no requests to repeat the questions yet. Oh, not yet. Connor says not yet. Okay, I'll take another drink. If you guys, in the about 30 seconds remaining, if you have any particular topics that you'd like to listen in future observatory talks, do let us know, and we'll see if we can make those happen as well. All right, so it's been 2 minutes. Thank you, Connor, for timing that. Let's move on to general trivia. Once again, as said, the training wheels are off. I'll repeat the question 2 to 3 times. Once again, if I go too fast, oopsie daisy. If I go too fast, you can let me know and I will slow down. Also, if you move past a question, let me know and I will also repeat the question. So here we go. Question number 1. Which planet in our solar system has the most moons? Which planet in our solar system has the most moons? Definitely not Earth. So there's one thing eliminated for you guys. Which planet in our solar system has the most moons? Question number 2. If you've ever been to an open house, I think I have said this multiple times, but the question is, what asterism is the Subaru car company's logo based on? What asterism is the Subaru car company's logo based on? So the Subaru car company logo actually shares its name with the telescope in Hawaii, called the Subaru telescope, made by the Japanese also. But also the car company and the telescope itself share their name with an asterism seen in the sky. It's visible during the summer, so you can actually go out and see this particular asterism as soon as it gets dark. Question number 3. What element on the periodic table was first discovered in the sun? This was done by examining the sunlight after passing through a prism. This particular process is called spectroscopy. So, once again, what particular element in the periodic table was discovered in the sun? It was done by examining the sunlight once it passes through a prism, and the process is called spectroscopy. The sun, in Latin, I think in Latin, shares its name with this particular element as well. Spectroscopy is a very, very important tool in astronomy. It allows us to not only see elements in a star, as this question suggests, but through those elements also tell us how old a star is. And spectroscopy is also used in other parts in astronomy as well, such as finding distances to galaxies. So the question is, what element in the periodic table was first discovered in the sun? This was done by examining the sunlight after passing it through a prism, and the process is called spectroscopy. Question 4. In what month is the Earth closest to the sun? In what month is the Earth closest to the sun? So the Earth's orbit around the sun is not a perfect circle. It is what we call an ellipse. So it is in the shape of an egg. So in some parts of the year, it's actually close to the sun, and in the other parts of the year, it is not so close. However, that is not how we get seasons. The seasons on the planet are decided by the tilt of the Earth, which is about 23.8 degrees, 23.5 degrees. Yeah. So in what month of the year is the Earth closest to the sun? And I'm not going to confirm or deny that I know I found the answer to this question just yesterday. So in what month is the Earth closest to the sun? Question number 5. A Venus day is famously takes longer than a Venus year. On the other end of the spectrum, which planet has the shortest day? So a Venus day is longer than a Venus year. And the question is to tell us which planet has the shortest day. So you have to think about, without looking it up on the internet, you have to think about which planet spins the fastest. Is it Earth? Is it Mars? Which planet has the shortest day in our solar system? And while this question is up, this particular question sort of reminds me of a recent discovery that happened where scientists, through a telescope called TESS, which looks for extrasolar planets or exoplanets, looked at a star, which is not really a ball, but essentially a pancake, which means it is super, super stretched out near its equators. And that's because the star is rotating very, very fast. But on top of that, they also found a planet near this star. But the planet, like our Earth, the planet does not go along the equator of the star, but goes along the poles of the star. Now, because the star itself is a pancake, the planet has essentially changes in seasons almost 4 times its orbit. So the planet observes about summer about 2 times and winter about 2 times in its orbit. But the surprising fact about this thing is that the orbit is only 36 minutes long. So this planet has 2 winters, which are about 9 minutes, and 2 summers, which are about 9 minutes. Once again, the question is, which planet has the shortest day in our solar system? Question 6. What was the name of the black hole in the movie Interstellar? What was the name of the black hole in the movie Interstellar? So the movie Interstellar had the depiction of a black hole, which involved scientists who actually crunched a lot of data. And until the Event Horizon Telescope actually came up with a picture of the black hole from the galaxy M87, that was the closest representation to a black hole that we knew of. And what we're asking you in this question is, what was the name of the black hole in the movie Interstellar? Question 7. So, what is the name of the comet visible by binoculars this month? It's just visible before sunrise, but later during the month, about July 23rd, July 24th, 22nd to 24th, it's going to be visible just after sunset. And we're asking you, what is the name of the comet? So maybe a time for a little shameless plug. If you follow us on our Facebook page, which is at Queen's Observatory, you would know the answer to this question because we posted a small info bit about this particular question or the answer. So maybe follow us on social media and you'll get answers to some of the trivia questions. Yeah, what is the name of the comet visible by binoculars later this month? It's right now visible just before sunrise, and later in this month, it will be visible just before sunset. I think you need binoculars. It's bright enough that you can make it out just by your eyes, but I think binoculars do a very, very good job in spotting this. Question 8. Saturn's largest moon, Titan, has lakes, clouds, rain, and other elements of the weather. However, the substance involved in all of this weather phenomenon is not water. What is the substance? Once again, I'll repeat the question. Saturn's largest moon, Titan, has lakes, clouds, rains, and other weather elements. However, the substance involved in all this weather is not water. And if it's not water, name what is it? I think it's Jupiter or Saturn, where I think the pressure is so strong that it rains carbon, but the carbon gets compressed because of the pressure and almost turns into diamonds, if I'm not wrong. Yeah, so the question is, on one of the largest moons of Saturn, named Titan, it rains, it has clouds and lakes, but not made up of water. What is the clouds and the rain made up of? Question 9. So this is a picture question. Featured in this picture is one of the programmers next to her code, which performed perfectly during the 1969 moon landing and likely averted an aborted mission. Name the programmer. So, if you remember our sound round, one of the sound clips was from a movie that depicts, well, not this programmer particularly, but the 8-year journey of actually coming to the 1969 moon landing. So the question is that we are showing you a picture of a programmer who did calculations, exact and perfect calculations of the 1969 moon landing. What was the name of this programmer? And finally, the last question, question 10, who coined the term dark matter, calling it Dunkelkalt Materie? As you can, I think this question has a hint in itself. Who coined the term dark matter, calling it Dunkelkalt Materie? Dark matter is a substance that is present all across the universe. However, it does not emit any light or react with any kind of light. Therefore, it's named dark. The way we know how that it exists is because of the gravitational interactions that it has in clusters of galaxies or galaxies. And so the question is, who coined the term dark matter, calling it Dunkelmaterie? You can imagine the name that is present over here sounds German to me. So maybe it was a German scientist. Maybe, maybe not. Who coined the term dark matter? Calling it Dunkelheit. Zach says he knows this one. Good for you, Zach. All right. So this was the last general trivia question. If you guys want me to repeat any questions, please put them in the chat on YouTube and I will repeat them. I'll give it about 30 seconds, after which we will move on to, I think, the double or nothing question. I'm sorry, next one is choose your adventure, choose your own adventure, and not the double or nothing. Apparently, James says the word search helps. The word search helps with one of these questions? Well, it does. It actually does help with one of these questions. We might have given it away in the word search. All right, so moving to choose your own adventure. So as I said, there are 4 different things that you could have chosen. You have chosen it before and not now after looking at the questions. So there's Marvelous Moon, which has the question, who was the last person to walk on the moon? Not the first, but the last. Who was the last person to walk on the moon? Cosmic Connection, what is the point of no return around a black hole? Called. What is the point of no return around a black hole called? And if you're not Matthew McConaughey, you're not going to end up at the back of your bookshelves. What is the point of no return around a black hole called? Zodiac Zone, to Anishinaabe, which is a First Nations territory and a tribe here in Kingston. What is the Pleiades constellation known as? To Anishinaabe, what is the Pleiades constellation known as? And finally, trivia track, which I think is the easiest one from these. Maybe Cosmic Connection is slightly easy. Anyways, so trivia track. What Star Trek movie featured the first entirely CGI computer-generated images sequence in film history? What Star Trek movie featured the first entirely CGI sequence in film history? I'm going to stay here for about a couple minutes. Not a couple minutes, that's too long. Maybe about 30 seconds for you guys to look at the questions. So the questions are, who was the last person to walk on the moon? What is the point of no return around the black hole called? To Anishinaabe, the Pleiades are also known as. What Star Trek movie featured the first entirely CGI sequence in film history? All right, I think we now move on to double or nothing question. I think this question particularly brings it super close to home. So if you've ever been around the Queen's Observatory, you ought to know the answer to this question. All right, the double or nothing question is, what year was the Queen's Observatory, at that point of time known as the Kingston Observatory, founded? What year was the Queen's Observatory, which at that point of time when it was founded, known as the Kingston Observatory? Name the year when the Queen's Observatory was founded. Okay, so that brings us to the end of all the trivia. We're going to go through the answers, but if you would like me to repeat any of the general trivia questions or the choose your own adventure questions, let me know. I'll give it again another about 30 to 40 seconds, after which we will call it an end to trivia. And the double or nothing question is what year was the Queen's Observatory founded? What year was the Queen's Observatory founded? So in this particular question, we're allowing you to actually give us plus or minus 10 years. You don't have to be exact. You can be 10 years off in either directions. What year was the Queen's Observatory founded? All right. So in about 10 seconds, I'm going to call it to the end of the trivia, which would mean pencils down, and we're going to try go through the answers. 3, 2, 1. Pencils down, everybody. Or if you were writing with a pen, pens down. Thank you for participating in the trivia. It's now time to actually find out how many points you all got. Okay, so we're going to go through the answers. Okay, so we're going to go through the multiple choice questions first, and then the general trivia, I think, and then the smaller rounds, such as word search. Not word search is actually pretty self-explanatory. Picture round and small questions. All right, question number 1. During what phase is the moon least visible from the Earth? The answer is new moon, and that is because it's not visible at all. And that's when the werewolves come out. The moon actually faces the shiny side of the moon, or the lit up side of the moon actually faces the other side of the Earth. Question number 2. What were Darth Vader's last words to Luke Skywalker? The answer, you were right. What were Darth Vader's last words to Luke Skywalker? The answer, you were right. Question 3. What is the name of the pattern found in the structure in iron meteorites? So there's a picture shown, and we were asking you what is the name of the pattern on those meteorites? And the answer is Windmannstatten, named after a Austrian scientist. Question number 4. How far does the average person walk in their lifetime? How far does the average person walk in their lifetime? And the answer is 5 times around the Earth. 5 times around the moon would be too small because the moon's fairly small. Jupiter is ginormous. And the orbits of the Earth around the sun is also pretty big. So 5 times around the Earth. Question 4 was, how far does the average person walk around in their lifetime? And the answer is 5 times around the Earth. Question 5, how long does it take light to travel from the surface of the sun to the Earth? And the answer is 8 minutes. So if the sun was to disappear right now, well, it's getting dark, so we probably would not see light for a while. But during the day, if the sun was to disappear, we would actually not figure it out for 8 minutes. Even now, we won't figure it out for 8 minutes. But yeah, during the day, if the sun disappears, we would not know for 8 minutes because it takes 8 minutes for the light from the sun to come to the Earth. Question 6. What is the name of Ripley's cat in Aliens? And the answer is Jonesy. What is the name of Ripley's cat in Aliens? And the answer is Jonesy. Question 7. When a planet appears to travel in the wrong direction, what is the motion called? And the answer is not reggae motion. That is what happens to you when you listen to reggae music. The answer is retrograde motion. When a planet appears to travel in the wrong direction on the sky, what is the motion called? And the answer is retrograde motion. Question 8, how far is the Earth from the center of the Milky Way? And the answer is 25,000 light years. So it takes light 25,000 years to actually come here. So when we look at the center of the Milky Way, we see it as it was 25,000 years ago. How far is the Earth from the center of the Milky Way? 25,000 light years. Question 9. In the movie Independence Day, while dragging an alien across the salt flat, actor Will Smith notably complains about what aspect of the alien? And the answer is smell. In the movie Independence Day, while dragging an alien across the salt flats, actor Will Smith notably complains about what aspect of the alien? And the answer, the smell. And the final question, which I think a lot of people voted the best question in the multiple choice, Alpha Alpha is a classic bad example for acronyms in astronomy. What does it stand for? And it stands for the Arecibo Legacy Fast Alpha Survey. It is a survey that is related to the Arecibo Observatory in Puerto Rico, and it is supposed to observe 25,000 galaxies, and it stands for Arecibo Legacy Fast Alpha Survey. So this was the multiple choice questions. I'll take 5 seconds if you guys want me to say the answer to any questions, but then we will move on to the sound round, if I'm not wrong. Okay, so the sound round consists of 5 sound clips, and we wanted you to, for question number 1, name the character. For question number 2, name the movie from which the sound wave was taken from. Question number 3, name the astrophysical phenomena that caused that sound. Question 4 was name the movie. And question 5 was a 2-part question, which was a song was playing and you had to name the song and the artist who created the song. So the first character talking in the first sound clip was Marvin the Martian. The movie in the second sound clip was Space Cowboys. The astrophysical phenomena that caused the third sound clip was gravitational waves. But if you wrote down black hole collision, we would also take that as the right answer. The 4th movie was Hidden Figures, which tells you an 8-year-long story that is leading up to the 1969 moon landing, where Neil Armstrong walked on the moon. Finally, there was a song, and the song was Fly Me to the Moon by artist Frank Sinatra. General trivia. So these were 10 questions where there were no multiple choice and you had to answer those questions without any help. Question 1, which planet in our solar system has the most moons, at least that we know of? And the answer is Saturn. Saturn has the most moons in our solar system. Question number 2. What asterism is the Subaru car company's logo based on? And the answer is Pleiades, or the 7 Sisters. What asterism is the Subaru car company's logo based on? Pleiades or the 7 Sisters. Either one we will take as the right answer. Question number 3. What element on the periodic table was first discovered in the sun by examining its light by passing it through a prism? The answer is helium. So sun is also called Helios, which is where the name helium came from. Question number 4. In what month of the year is the Earth closest to the sun? And the answer is January. You can actually try to Google this question and see how the sun appears from the Earth. They took 2 pictures, one during June and the other during end of December, start of January, and you can see actually that the sun is genuinely bigger during the month of January. Question 5. A Venus day famously takes longer than a Venus year. On the other hand of the spectrum, Which planet has the shortest day? And the answer is Jupiter. A day on Jupiter is only 10 Earth hours. A day on Jupiter is only 10 Earth hours. I would not get a lot done if I lived on Jupiter. What was the name of the black hole in the movie Interstellar? The answer, Gargantua, because it was a big black hole. That wasn't the reason. What was the name of the black hole in the movie Interstellar? The answer was Gargantua. Question 7. What is the name of the comet visible by binoculars this month? Right now, it's visible just before sunrise, and later it will be visible just after sunset. And the answer is NEOWISE C2020 F3. NEOWISE is the telescope, and the object visible is the C2020 F3. NEOWISE is a telescope launched by NASA, which looks for near-Earth asteroids and studies them. Question 8. Saturn's largest moon, Titan, has lakes, clouds, rain, and other elements of the weather. However, the substance involved in all this weather is not water. What is the substance? And the answer is methane. Question 9. Featured in this picture is one of the programmers from A Next to Her Code, which performed perfectly during the 1969 moon landing and averted an aborted mission. Name the programmer. And the answer was Margaret Hamilton. Margaret Hamilton was the answer to this question. Finally, question number 10 is who coined the term dark matter, calling it Dunkelkalte Materie? And the answer is Fritz Zwicky. He was a Swiss-American astronomer. And if you did the word search, you also got the answer to this question. James asked, can we get half points for her first name? Sure, James. Half points for question 9, if you just guessed the word Margaret or Hamilton, you get half the points. All right, so this is question 10. Who coined the term dark matter, calling it Dunkelkalte Materie? The answer, Fritz Zwicky. The answers to choose your own adventure. Who was the last person to walk on the moon? The answer, Eugene Cernan. He was a part of Apollo 17, and he was the last person to walk on the moon. What is the point of no return around the black hole called? Answer, event horizon. To Anishinaabe, the Pleiades is also known as the Bughunazaag Jig, hole in the sky. What Star Trek movie featured the first entirely CGI sequence in film history? The answer, Star Trek: The Wrath of Khan. So, double or nothing question. What year was the Queen's Observatory, at that point of time known as the Kingston Observatory, founded? And the answer is the year 1855. If you go to the Kingston cricket field, which is right behind the Bioscience Complex here in Kingston, you will see a plaque that commemorates the first location where the Kingston Observatory, which is now called the Queen's Observatory, is situated. So if you had anywhere between 1845 to 1865, you can give yourself the double the points. All right, so we're now going to go through some of the quick questions. So the first part of the quick questions was, we gave you a title which was synonymous to a movie title, and you had to name the movie. So, Heavenly Body Battles, The Strength Stops Sleeping, refers to Star Wars: The Force Awakens. Booty World refers to Treasure Planet, because pirates call treasure booty. Complete Remembering refers to the movie Total Recall, near misses of tertiary type refer to close encounters of the third kind. And finally, males in dark clothes refer to men in black. The picture round had 4 pictures. For the first picture, you had to name the telescope and the movie. And for the second, third, and the fourth picture, you had to name what objects you were seeing. And so, for the first picture, the telescopes were the VLA in New Mexico, called the Very Large Array, which is a composite of multiple radio dishes, and it is from the movie Contact, a brilliant movie. If you have not seen it, I highly recommend it. The second image is taken in Mars, and it's taken by the Curiosity rover. It is the rover that can take selfies. The third image is of the Crab Nebula, and which is also a Messier object. And the fourth image is for the constellation Draco. All right, so that brings us to the end of the trivia night. If you could let us know in the chat how many points you got, that would be pretty cool. Connor, what's the total points? I will also let Connor come online now. I will stop sharing my screen, and maybe Connor can come online.
Hello.
Yeah, Connor, we can hear you. If you can go into gallery view, that would be great.
Yep. Okay.
What were the total points?
Well, the total's out of 40, but there are a few bonus points to get it along the way.
Okay. All right, so the total is out of 40. So in chat, please let us know how many points you got. Yeah, Connor is the one who came up with most of the questions. So once again, thank you, Connor, for doing that. Yeah. It looks like there were 2 things that could not be found in the word search, which were Thorne from Kip Thorne and Sandage from Alan Sandage. That seems to be a bug.
Sorry about that. I didn't realize that word search generators sometimes just decide not to include some of the words you give them.
Yeah, that must be a bug. But yeah. So Connor, what's next in the store for us?
All right. So thanks again for everyone joining us for Dilraj's talk and the trivia. And in order to round this off as an observatory event, we kind of wanted to get an observing element in there, although everything's virtual. So what we're going to do is use a virtual software that lets us pretend to do some observing, and we'll see what sorts of things we could have seen tonight. And if anyone wants to tell me their birthday, we can go back in time and figure out what the sky looked like for them. There's all sorts of cool things that we can do with the video system that we couldn't do with the observatory. So in that way, it's kind of fun and special that we're in the virtual setting. But of course, we would like to be at the observatory right now, seeing it for ourselves. All right.
It's the second best thing to what we can have in this situation. Connor, if you can make me host so that I can control the background,
right,
logistics, and you can run the observatory. Oh, wow. Kevin Tell got 32.5 out of 40.
Wow, that's really good. There were some pretty tough questions in there.
Yeah.
I had fun writing them and looking them up. There's a bunch of stuff that I learned making this, which is also fun. Apparently, when Will Smith was dragging the alien in Independence Day, the salt flats that they were dragging on apparently actually smelled really bad. And it wasn't scripted that he would complain about the smell, but it was just a really hot day and he was really upset and he just yelled out, "What's with that smell?" And they kept it in as part of the video.
Wow. Mark Richardson, 38.
38 for Mark. Wow. You're nailing it. All right. I think more like 25 to 30 is those are good scores for for people who aren't super involved in their astronomy trivia. Word search needed more time. Yep, well, I needed more time to make it apparently as well. All right, so I am going to, let's see, I'm going to share my screen so that we can, have you made me co-host? Yeah. And I'm going to switch to view the Stellarium software package, which, by the way, anyone can use Stellarium. It's free. You just have to download it from their website. And it's really not that hard. It works on just about any operating system. I actually use Linux for my operating system. So if it works there, you know that it probably works on yours. All right, so what we're seeing here is sort of the baseline Stellarium view. And it's just basically what you would see if you were standing in a field right now. But we can play around with the time. So if I go over here, click on the date time window, this shows what time we're at right now. And so if I want, I can just jump ahead an hour and the stars start coming out in an hour. And we'll see an hour from now, if you want to go out on your porch, looking in the southeast, you'll actually see Jupiter and Saturn right beside each other. And they're bright enough that you'll see them just about any time. And so they're definitely something that we would be looking at the observatory with at least some of our telescopes.
It's a pretty cloudy day today, so probably not going to see Jupiter and Saturn.
Oh yeah, yep. Not
but
today.
If you're not in Kingston and somewhere else,
if you're in the Northern Hemisphere, now because this is virtual and not in person, we can get the computer to do some work for us. So first thing, let's go down to the bottom here, and there's a bunch of options. I'm going to turn on the constellations. So now we can see where in the constellations everything is. So Jupiter and Saturn, they're kind of in the Sagittarius constellation at the edge of it, with whatever that one is. I'm an astronomer, but I do not memorize all of the constellations. If we look around, we can see the other constellations, Vulpecca, Cygnus, Cassiopeia, that's one that I can recognize. And now let's jump another hour ahead. And now it's gotten dark, and we can see that the Milky Way is starting to spread across the sky. And actually, just one second, you might hear a little whoosh. Okay, yeah. All right. Now over here, we can see Ursa Minor, which is nice, and Ursa Major. These are ones that you can kind of pick out very easily for yourself. Now also, because this is virtual, we can pretend that we have a wide angle lens for our eyes. And if I zoom back, we can sort of see more of the sky all at once, which is a little trippy of a view to look at first, but it kind of helps you lock in and find some interesting things to check out. Now, another way with this software, if I was, this is the software that I use to plan sort of what we're going to be looking at with the observatory. And right now I see a bunch of stars, but we don't like to look at stars because no matter how good your telescope is, it's pretty much always just a dot. There's only a couple stars that have ever been actually imaged with any sort of resolution. So what I can do is turn on deep sky objects. And this will now highlight everything in the sky that is brighter than a certain value and are possible targets that we could look at. And right away, that highlights something right here in the middle in the Hercules constellation. These two dots here, if we sort of zoom in on those a little more, then this name pops up here. the great star cluster in Hercules. That is something we would definitely be looking at. And today we can look at it even though it's cloudy, because we are using a virtual system. And as we zoom in further and further, they actually have a little picture in the software so that you can see what it looks like. And the great star cluster in Hercules is an example of a globular star cluster. So a globular star cluster is a really tightly packed ball, in this case of somewhere around 1 million stars. And that tightly packed ball of stars is orbiting around our whole galaxy. It's like its own little mini galaxy orbiting our bigger galaxy. And you'll also notice that everything's sort of moving with time, and that's just because the software is simulating the rotation of the Earth, and so everything in the sky appears to be moving in the opposite direction to the rotation of the Earth. And so every now and then I just have to grab it, pull it back over. There we go. And so these globular clusters are really, really quite packed together. It's only, the width of the whole thing is only about the distance to the nearest star from us. So from our sun to the nearest star to us, that is very similar to the radius of one of these clusters, which is just amazing to think that there might be 1 million stars packed in that same distance, maybe twice that distance, but really even if it was twice that distance, that would be very packed. So these globular clusters are very fun to look at, and you can sort of see the sort of fuzziness to them, and a few of the stars here are bright enough that you'd be able to pick them out individually among the sort of haze of other stars that we would see. I'm just gonna jump over. Okay. So we zoom back out. What other things? Oh, you might see this one here, M92. Whenever there's an M and then a number, that's usually the Messier catalog. And Charles Messier, back in, I think, the 1800s, although I'm not sure, he cataloged a whole bunch of objects that amateur astronomers and professional astronomers alike love to study all the time, because they're relatively bright compared to some of the other things that our high-powered surveys can find. But because they're bright, that means we can study them in very good detail. So this one is another example of one of those star clusters. I can click on it and get a little bit of information. A lot of this information won't be too useful, but right up at the top, you get the type. It's a globular star cluster, like that great Hercules cluster, although this one you can see looks a bit smaller to us. Magnitude 6.4. So the magnitude system is funny. The bigger the number, the harder it is to see. The smaller the number, the easier it is to see. And so 6.4, that means that as long as you're not like in downtown Kingston with lots of light pollution, just about any telescope, even if it's like a little $100 one, that'll let you see this in varying degrees of quality depending on how good the telescope is, but you can definitely find it with just about any telescope. So magnitude 6.4, that's probably as far as you'll go with a really tiny one. If your hands are very steady, you may even be able to see it with binoculars, but I wouldn't try and push it. I would just go for the great star cluster in Hercules. That one's very easy to find and very cool looking. Let me see. So right here, there's that Draco constellation. That was one of our questions. And I actually used the Stellarium software package to get the image that we used for the trivia night. And so you can play around with the thickness of the lines and stuff in order to make pretty pictures. If anyone wants to put their birthday, if they're brave enough, in the chat, then I can change the time to be whenever that was. Let's see. In the meantime, I'm going to say, well, it looks like there's a whole bunch of stuff going on here. So let's zoom in on this. And let's see if I recognize any that might be cool looking. Well, we won't be able to see this, I think, at any point with the observatory, but why not zoom in on this Eagle Nebula while we have access to the digital version. Here we can see some of the pictures start popping up that Stellarium has. And if we keep zooming in, you might notice something kind of familiar about this Eagle Nebula, because right in here, that's the Pillars of Creation, one of the more famous photos that have come out of the Hubble telescope. And actually, this is one of the things that the upcoming James Webb Space Telescope is going to be looking at, because all this beautiful gas and dust that we see, as beautiful as it is, it's blocking something that's very interesting to astronomers, which is the formation of new stars. How are these new stars being created in this gas and dust cloud? Well, we can't see that because what we can see is the gas. The James Webb Space Telescope is going to be looking at a different wavelength of light that doesn't get blocked by this gas and dust. And so we'll be able to see right in at these stars as they're forming. There's a few different places where we're going to do that. So that's a very special little nebula right there. All right. If we scroll over here, the Trifid Nebula, I don't know much trivia about that one, but I do know that it's very pretty, and it's one that is too faint for us to see at the observatory. But yes, let's see. This one, it's magnitude 6.3 as well, so it's about as bright as that other cluster. But the trick is, although it's just as bright as that other cluster, it's much bigger on the sky. So it takes that same brightness and spreads it out so wide that at any one point, it's very dim by comparison. So we wouldn't be able to, our eyes would be collecting the extra light, but we wouldn't actually be able to pick out the features of this nebula. You'd probably, in order to get this one, need to set up a camera, connect that to the telescope, let the camera take many, many, many pictures of this nebula, and then add them all together. And when you do that, then you can get pictures of very, very faint things. That's actually how a lot of these pictures are created. All right, let's see. So if I was going to plan for the observatory, I would say that we probably would look at Jupiter and Saturn. I don't know if Stellarium has very good versions of Jupiter and Saturn, if we can get a look. Because seeing Saturn for yourself, Saturn is one of the jewels of the sky, and you have to, at some point in your life, get a good look at Saturn through a telescope. It's quite bright, so just about any telescope will do, as long as you're not downtown. And let's see, oh, there we go. So it does actually have a view for us. There's Titan, that moon that has its own weather, and a whole bunch of other moons around Saturn that we can see. Some of the brighter ones. It doesn't include the full list in here, but it'll show us a few of the more famous ones. Same for Jupiter. So let's scroll over to Jupiter and see what we would see if we looked at it at the observatory, although we have to contend with the atmosphere that this program doesn't have to contend with. So it might be a little trickier. So these bands that you see across, almost like just off of the equator of Jupiter, we have seen those at the observatory. And also these moons around here, you can very easily pick out the four moons that are the brightest, called the Galilean moons. Those are the ones that Galileo discovered. and it got them in a lot of trouble because they clearly weren't orbiting the Earth. And at the time, everything had to orbit the Earth because the Earth was the center of the universe. So that wasn't good. All right. So yes, Jupiter, Saturn, the Great Hercules Cluster, those would all be excellent things for us to look at the observatory. I'm just gonna get rid of that information there. And let's see, it might be coming out a bit late, so I don't know if we would get to see it at the observatory, but the Andromeda Galaxy is just on the horizon right now, and that's another one maybe later in the summer that we'd love to look at. This is the nearest large galaxy to the Milky Way, and there we go. They've got a picture of it here along with one of the satellite galaxies of the Andromeda Galaxy. And this you can see from the observatory. Mostly you see the center and maybe a little bit of the structure along the edges, depending on how good your eyes are. The full length is actually 7 times bigger than a full moon. So the Andromeda Galaxy is actually gigantic on the sky, and it actually doesn't fit in the observing window of our telescope. You would have to look at a whole bunch of different parts individually and add them together sort of in your head. But yes, Andromeda Galaxy is a really special thing to look at. It's actually going to collide with our Milky Way in about 4 billion years, but hopefully that won't be too big of an issue. In fact, most likely it won't bother us too much, not just because the sun will have died at that point, but also because when 2 galaxies collide, it's actually very rare for any stars to collide with each other. Like I said, the nearest star to us inside the Milky Way is really quite far. It's more like what is it, 4 parsecs, something like that. So that's actually a huge distance compared to the size of the sun. And there's lots of room for many stars to fly right in between us and the nearest star. And that's what most of them will do. There's likely no collisions between stars during the collision of a galaxy. And actually, it would probably just be very cool to watch. The Andromeda Galaxy would get bigger and bigger on the sky until it would be basically as big as the Milky Way. And then they'll start warping each other because of all the gravity. Lots of fun, but it takes place over hundreds of millions of years. The Heart Nebula, I just spotted that one over there, and that one's fun. Maybe around Valentine's Day, although it would be hard to get a picture. You can find pictures online, and the Heart Nebula roughly looks like a heart. I'm not going to try and trace it out because I'm not seeing it very well. There are better pictures online that show you the Heart Nebula. Oh, thanks, Simran, for the comment. Yes, when the Milky Way and Andromeda collide, we've already figured out what it's going to be called, and we're going to call it the unfortunate name of Milkdromeda, because astronomers are bad at naming things. Not just acronyms, but just names in general. We're pretty bad at that. All right. So one other thing that I like to do, because we have this software here, is show some of the effects of the atmosphere for astronomers. Astronomers taking pictures of things in the night sky are constantly competing with the atmosphere, which, thanks to little bits of moisture in the air and wind currents, tend to kind of blur our image of whatever's out there. But in software, we can actually just turn that off, and suddenly everything becomes much clearer. So you can see very clearly the Milky Way across the sky here. If you haven't seen the Milky Way, you really need to. it's not too hard. You just need to find a dark location. Driving 30, 40 minutes north of Kingston will get you to a dark enough location as long as you're at the right time of the year. It seems like right now would actually be a pretty good time of the year. So you can see the Milky Way across the sky. But if we wanted to plan out what's a really good day to see the Milky Way, then what we can do is just start with our view. Let's turn off the deep sky objects because that's just making it complicated. All right, so now we can go to our date time window and try changing the day. And so what it did is just jumped one day forward, but the same time at night, which is 11 o'clock. And we can keep doing that. And it looks like the Milky Way is, with time, getting out of the view. So right now, at 11 o'clock on July 11th, we'll essentially be looking directly away from the center of the Milky Way. And there's not too much there, except the deep void between galaxies. All right. We keep going forward, keep going forward. Oh, I think I was changing the month and not the day. But anyway, the point holds. With time, you get better views of the Milky Way. And let's see, where are we going? So if I keep changing the day, oh, there's the moon traveling across the sky. If you want to see the Milky Way, you want to pick a time when the moon is not up, because the moon is actually pretty bright, kind of like light pollution in a city. It can cause you to not be able to see very much dark stuff. Oh, there's the moon again. And so as you can see, with time, the position of everything in the sky sort of changes. Although these are all at the same time of night, it's the Earth that's moving around the sun that's sort of giving us this bit of time lapse here. We can also change the year. And so if I go up in year, you see we come back to roughly the same point each year, but not exactly. And so it kind of has a bit of a wobble. The moon also doesn't really track with each year. So it's got its own timeline. You can see Saturn and Jupiter sort of moving where they are in the sky as well over time. Oops, I'm changing month now. Let's go back to changing year. So, oh, and there's a Uranus up here. And that one's changing its location over the years. Okay, now let's see what happens. What if we go a lot further? What if we go, instead of the year 2066, the year 12,066? And let's see, the changes might not be super easy to see. So what I'm going to do is I'm going to focus on Ursa Major. And let's see what happens when we go very far into the future. So let's look at, instead of 12,066, 102,000. Whoops, I've lost it. Let's just go to our search. And if we look up the Big Dipper, that'll take us to it. And what you can see now is that it's very much changed shape. This star here has sort of moved further out, and it's not that nice scoop. And also the handle has sort of bent a little bit because the stars are moving. We call that proper motion. It's the motion of the stars on the sky, although over very long times, it's also probably moving away from us and all sorts of stuff. These stars are all kind of shuffling around in the Milky Way, although we are kind of roughly orbiting together. So yeah, over time, the stars sort of move around. And I think that's the last thing that I wanted to talk about, is sort of what happens to the stars over very long time periods. And I wanted to show you what we would look at. Let's move this back to 2020. Okay, so that's back to what we're looking at now. So if anyone has any questions, feel free to ask. But I mostly just sort of wanted to show what's up in the sky right now? What does it look like when time changes a lot? And what our atmosphere does. So if you ask an astronomer, we should just get rid of the atmosphere on Earth. It causes too many headaches. All right. I'm not seeing any questions. So I think we're going to end the live stream. There's about a 30-second delay, so I apologize if you ask a question right at the last minute. We might not see it.
We could answer those in the chat.
But yeah, we
chat
could go back and answer the questions. Again, the software is Stellarium. You can get it for yourself very easily and sort of see what's out in the sky. The controls are very, very easy to use. You can change the time just by clicking on the clock. You can search for things by looking at the magnifying glass. And at the bottom, you can change a little bit of what you're seeing, including art for all of the constellations, which is kind of fun, but also kind of gets in the way of what you're trying to look at. All right, I'm gonna stop the share right now, and we'll go back to the chat. All right, well, thanks everyone for coming out, and thanks for those of you who stayed all the way to the end of our Stellarium session. I hope you learned some fun trivia. I hope that you learned some cool science from Dilraj and maybe some cool stuff that you can do at home on your computer with Stellarium. So thank you all for coming out.
Yeah, thank you. Okay. See you guys next month.
Yep, so we always go on the second Saturday of the month, although if Saturdays aren't a good time for people, maybe we'll try moving it around. We will make sure to get the word out. We have email, we have Facebook, we have Twitter. We're gonna make sure that everyone knows when the next one's gonna happen.
Yeah.
All right.
All right. Thank you guys for coming.
Thanks for coming out. All right. I guess I'll just applaud Nick. Good job hosting.
Thank you, Connor. Thank you for making questions.
It's a little awkward with just two people, but all right. Do you want to end it, or do I end it?
You have to kill the live stream.
Okay. All right. Bye, everyone.